Hi, I want to explore the graphical representation of Goldbach partitions. This complements my other video, the solution set of Goldbach's conjecture, which suggests that the conjecture is susceptible to elementary set theory. The reason it is because of the regularity in the distribution of primes when partitions are considered to be elements of sets. I'm going to explain just how simple and regular the distribution is, and the secret twist that makes it appear complicated. So what is it that creates the structure of Goldbach partitions when we view them graphically? It turns out to be quite simple. Consider the even integers and subtract for each one the smallest odd prime beginning with 3. If the difference is a prime, we have a partition. If not, we do not. Now here is the interesting thing. Look at the blue columns. The differences are the primes in order and with the gaps between them exactly as they are in the counting numbers. So we have 3, 5, and 7, and then a gap for 9. We have 11 and 13, and then a gap for 15. We have 17 and 19, and then a gap for 21. We have 23 and then a gap for 25 and 27 and so on. Now we can continue with the subtraction of 5, 7, 11, 13 and so on. In each case, the first occurrence is for a greater even n. Of course, this is because the prime cannot be greater than n minus 3. There are some other properties we'll look at later. When we zoom out on the partition structure, we see the elements are strictly organized into paired columns of recurring elements and sequential elements. This arrangement does not exist because I've written the algorithm for building the graph a certain way. It's simply the inevitable consequence of subtracting the smallest prime from each even integer as shown in the previous slide. This happens to be by far the simplest way to find partitions algorithmically. But that misses the point because this arrangement is self-disclosing. If this graph is new to you, you may or may not get its beauty all at once. But it should banish right away any notion that the partitioning of even numbers into primes is somehow mysterious. Now here we look at the question of element alignment, which should already make sense if you understand the simple rules that give rise to the structure. Rule number 1. The largest prime of a partition is half n. If that's true, then the gaps between the quote-unquote top primes in this graphic must be prime gaps of the counting primes. Rule number 2. The prime sequences that follow must also follow the prime gaps of the counting numbers. The recurring elements must align with the sequential elements. It's not that the recurring elements do not exist in the gaps. You can consider that they do, but not as partitions. I want to mention another feature that the sequential prime alignment produces. The complete partition is given by the first prime in the sequence and the aligned prime. That is, given any even n, the sum of the prime aligned with it and the first prime of that sequence is equal to n. So one example in the slide is the circled 7, the first prime in the sequence, and 23, the prime aligned with 30. Needless to say, they are a partition of 30. It's not in the least surprising when you give it a moment's thought, but it's worth pointing this out. Partitions are the alignment of elements, in graphical terms a recurring element and a sequential element. But wait, it's not quite that either. It's merely the alignment of a sequential element. If a sequential element is aligned with an even integer, there is a partition. It's that simple. The recurring elements, quote-unquote, come into existence if there is a sequential element. It's a kind of superposition principle. That's the key that unlocks either the complexity or the triviality of Goldbach's conjecture, depending on how you think about it. So far, we've looked at the structure as being a set of vertical and horizontal elements. But the structure is also a set of diagonal elements. In fact, every element is a member of the diagonal set that begins with 3, the smallest odd prime. The diagonals can represent both the recurring and sequential primes. Now, the significance of the diagonals is they are not localized to one partition locus. Diagonals traverse the graph, intersecting the loci of multiple even n's, from n-3 to 2n. Can we show that of the set of diagonals, there's a sequential diagonal element that intersects every n? We can look at a partition intersection as the solution set of 3 lines. For every even n, there must be at least one diagonal locus for which the recurring and sequential primes are equal to those of the vertical and horizontal lines of partition elements. This intersection is, in fact, the same partition. Therein lies the solution to Goldbach's conjecture.